Hi, welcome to video 9 of linear relations. We're going to be looking now at linear and nonlinear relations just to see the difference between those and how we can determine which are linear and nonlinear by looking at a graph, a table of values, or an equation. So we just want to recall a few things here at the beginning. So a linear relation is one that forms a straight line. I know we don't need the word straight. Mathematically. So it forms a line when graphed. A table of values represents a linear relation if the finite differences are the same for every row in the difference table. So we looked at that in previous videos. You can write a linear relation. Now this is one we just looked at. This was intercept form that we looked at. There is y equals b plus mx form, which is intercept slope form. And this other form here, we haven't looked at yet. This is called standard form. And that's basically if we were to take this c from the intercept form and just subtract that value from both sides of the equation, we would end up getting this equation here, which is called standard form. Okay, we'll look more into that a little bit later as well. Table of values represents a non-linear relationship. So here's the difference between the table of values representing linear relation up here. If the finite differences are not the same. Okay, so that's just something to pay attention to. Finite differences are not the same for a non-linear relationship. And the degree of the term is the sum of exponents in the term. So we've looked at this briefly in section 2.4. We'll take another glance at it again today as well. Okay, so here's some of the terminology that we're going to need. Now we'll take a look at some different tables, graphs, etc., and we need to identify whether the relation is linear or nonlinear. So first of all, we'll take a look at this table of values. As you know, the x column is the independent variable and the y column is the dependent variable. Notice that the independent is always on the left side of a vertical column and the dependent is always on the right side or the right column. Importantly, in order to determine if this represents a linear relation or not, we have to make sure, first of all, that the independent values are increasing by a common amount, just to make it a little bit more apparent. So if we were to subtract 4 minus 2, we see that we get 2 here, 6 minus 4 is 2, and 8 minus 6 is also 2. So because those are all constant, then we can quickly look at the dependent side and do the same thing. This is where we're going to do the finite differences, or the first differences, and we're going to see if this will tell us if it's linear or nonlinear. So 3 minus 5, that would be negative 2. 1 minus 3 is negative 2. And negative 1 minus 1 is negative 2. So because these are all constant, then that means that by looking at the top here, we see the table of values represents linear relationship if the finite differences are the same for every row in the difference table, which we see that it is in this case. So in this particular example, this is an example of a linear relation. Part B, we're looking at a graph. Well, we can tell that's a line. Okay, so since that is a line, we know that it is a linear relation. And we know also that line is the root of linear. So therefore, that makes it a little bit easier to determine as well. Over to C, well, this is not a line. Okay, so it's not a line. Therefore, we say it's nonlinear. And this is actually a curve. Okay, so we never say it's a curved line, we just say that this is a curve. So we know it's not a line because it's not straight. It is a curve, and that means it is nonlinear. Going down here to part D, Well, this is a standard form of slope y-intercept. This is the slope. So the coefficient in the variable term is slope, and the y-intercept is that whole part, including the sign. So this is the y-intercept. So that's a common form that we've seen already. It can also be written like this. I always like putting the y-intercept first, because that's the first thing that we plot if we're actually going to plot the line, draw the graph of the line. So I just change those around because we know that order doesn't matter when you add. You could do 4 plus 3 or 3 plus 4, and both of those obviously equals 7. So it doesn't matter the order that you add things. So that's why we can change the order of the variable term and the constant to have it written as the constant and then the variable term. Okay, and because of this, we know that this type of equation comes from table of values or comes from certain scenarios that we've looked at in past videos. Therefore, we know that this is linear. Okay. Part E, we looked at this in the last video using x and y intercepts. If we were to solve for to get the x-intercept, we would set y equal to 0 because anywhere along the x-axis, y does equal 0. So we'd be left with 4x equals 2, and then x equals, well, we'd have to divide that. So x is 2 over 4, which can be simplified to 1/2. So if we were to find the ordered pair of the x-intercept, it would be 1/2 and 0. And then we do the same thing for the y-intercept. Not that that's really important in this particular case, but this is how we do it, just as a little refresher from last video. We know anywhere along the y-axis, x equals 0. So the y-intercept would have a coordinate of x equal to 0. So when you substitute 0 in for x, we end up getting negative 3y equals 2. Therefore, y equals negative 2 over 3, because we divide both sides by negative 3 to isolate the y. And then the y-intercept is 0 and negative 2/3. Okay, so this is the form of a line. This is representative of a line, and so this is linear. And then if we go over to part F, to standard form, well, this is basically the same form as linear, or sorry, intercept form, except that the constant is now on the same side as the other variables, and one side is just equal to 0. So because it's basically the same form as intercept form, as I told you above, this is called standard form. It's very similar to intercept form, and therefore we know that this is linear. Okay, so now we move on to some other function. What if for well, it is called a function, but we have some other relation here, and this relation is y equals x squared. And we want to take a look to see, well, is this going to be linear or not? So if we were to take this value of x and substitute it in for y here, we know y equals, well, x is negative 2, and that's squared. That gives us a 4. Y is negative 1 squared, which is positive 1. Y is here 0 squared, which is 0. And then y here is, again, positive 1 squared, and that also gives you a positive 1. So if we were to plot those points on the grid on the next page, actually, I'm going to go one step further here, and I'm going to add in one more row, and I'm going to put in positive 2 here. And then I'm going to say y equals positive 2 squared, and that equals 4. Okay, so the points I'm going to be plotting on the grid on the next page, well, the x here is negative 2, so I'm going to be plotting the point negative 2, 4. Then I plot the point negative 1, 1. Then I'm going to plot the point 0, 0. And then 1, 1. And then here 2, 4. Okay, so on the next page, I'm going to plot these points. So follow along, please. Okay, so so we're going to graph these. So there was a point -2, 4. So we're going to plot that here. And then there's a point -1, 1, which is plotted right there. 0.00 is right here. 0.11 is here. And +2, 4 is right here. Okay, so those are the points. And if we were to join them with a curve, we would see that, if I can draw this well, that the line, or sorry, the points get connected like this, and as you can see, that is nonlinear because we know it's not a line, and here's the prediction, x equals 2. Well, I already added that into the other page on the table of values. So when x equals 2, y equals 4. And this last thing, had we not put it into the table of values, we would be extrapolating this because we were kind of using the first 3 or the first 4 points and then kind of following along the pattern that we were developing and hoping that it would continue in the same manner, therefore extrapolating the graph to incorporate the point 2, 4. Okay, so if we look at this equation, y equals x squared, well, we have to then go back and think degree of a term is the sum of exponents in a single term. Okay, so if we had some term that were x squared y to the power 4, then the degree of this is going to be 6. Okay, it's the sum of those exponents. And the degree of an equation is the highest degree of any term in the equation. So suppose now if we take a look and say we've got 3x squared y minus 5x to the power 4 y cubed plus 1/2 x y to the power 4. Well, then we can take a look at the degrees. So the degree of this term, is 3, because we know there's an exponent of 1 there that we don't see. The degree here is 7, because we're adding those two exponents. And the degree here is 5, because there's an exponent of 1 there that you don't see. So the degree of this equation is actually 7, because that's the highest. It's the highest degree of any of the terms in the equation. Okay, so keeping all that in mind, let's take a look at this. And so before we get into this, take a look at this. Equation, y equals x squared. What do you know that's different? What do you see that's much different from that equation than these 3 equations over here? When we've got y equals 3x minus 2, 4x minus 3y equals 2, or 0 equals 3x minus 2y plus 12. I know all of these have more terms than the last one, but what's very different from these all are very common. And then this y equals x squared is different than those other equations, especially because of the fact, well, this is nonlinear, and all of those other equations that we're looking at over here, these are all linear. So what's so special about y equals x squared that makes it nonlinear, where all these other equations are linear? So basically, we're looking at, well, and I mean, of course, the exponents thing might give it away as well. We've got an equation here where the exponent is 2. Here we've got the exponent of 2 and 3 on x and y. Here's the exponent of 2. That exponent is 1. There's an exponent of 3. Here we see these exponents on variables are just 1. There's 3 and there's 2. So if I take a look at all these, so for this equation here, we see that's the highest exponent that we see, and the exponent here is 2. Here the exponent is, well, the degree is 2 plus 3, which is 5. Here the degree is just 2. Here we see that there's a 1 there that's not seen. That degree is 1. Here the degree is 3. Each one of these, well, those are from different points, or sorry, different terms. So the degree is just the highest exponent of any one term, and because these are different terms, we don't add them together. So the degree there is 1. Here the degree is 3, and here the degree is 2. I'm going to add one more here, just to be tricky. Y equals 3 squared x plus 2. Okay. Now, what's the degree, or what's the exponent on the variable? Well, this is the thing that we're more worried about. We're more worried about the exponent on the variable, not on the coefficient. So that's just a coefficient. And so that would be just a little bit of a trick if it were 3 squared. But 3 squared we know is just 9. So therefore that equation can just be written as y equals 9x plus 2, where the exponent on the x is still 1. Okay, so it's the exponent on the variable that we're more concerned about. Okay, so don't worry about getting tricked by the exponent on a coefficient or any other kind of constant. So from before, y equals x minus 1, well, we know that was linear. That's y equals, that's slope y-intercept form, so that's linear. And this other equation down here, that's an intercept form, and we know that's linear from the last video as well. And notice that the exponent, or the degree, is just 1. And then if we look at all these other ones, degree of 2, degree of 5, degree of 2, degree of 3, 3, 2, all of those ones do not have degree of 1, just like up here, the equation y equals x squared, this is called a quadratic, and the graph itself is a parabola. Okay, so it's a curve, it's a specific type of curve called a parabola that you learn more about in grade 10. That is a quadratic equation, or quadratic form of a curve. And the degree is 2. And we notice that that's nonlinear. Okay, so we know that is nonlinear. This degree of 2 is nonlinear. And obviously this one. So if they're degree 2, they're nonlinear. And I would then, of course, hazard a guess that anything that's not 1 would be nonlinear. So a degree of 3, well, a degree of 3, this graph here, would kind of look like this. Okay, that one kind of looks like that. This one actually looks exactly like that as well. The one that's just above it is probably stretched a little bit more vertically. But they both have the same sort of look. This y equals this graph itself is actually, it looks very much similar, but a more complicated degree of 5 would actually kind of look like this. It would be a little bit more loopy, okay, and it would look like that. But this specific one actually is kind of boring. It kind of just looks like the cubic here. But anyways, these graphs of degree 2 and 3 and 5, those are nonlinear, and you can tell that with the fact that the degree is not 1, it shows as nonlinear. Whereas these other graphs with degree 1, those ones are linear. So this one looks something like this. Whoops, it shouldn't go through the origin, so that's my bad. Actually, maybe I'll just redraw that one. There, that's better. And this one will look something like this. Okay, so linear has a degree of 1. Nonlinear has a degree of anything but 1. Okay, so that's the big takeaway here. Equations of linear relations have a degree of 1, so the exponent is 1 on the variables. That's the highest exponent it can have on any variable. And nonlinear is the degree that is a degree that is not 1. Okay, so it could even be negative. Okay, but we'll get into that later on in the future as well. Okay, so that's basically a bit of a nutshell of linear and nonlinear. I'll just do a very quick summary here. I know this video is going way longer than it should. So for linear relations, in the table of values, the first differences are constant. And a graph is going to be a line. And an equation, the degree is 1. Okay, remember, degree is referring to the exponent on the variables. Okay, so you can't have any variables with an exponent that's not 1. Okay, and then for nonlinear, it's just the opposites of all these. First differences are not constant, the graph is nonlinear, and the degree of an equation is something. There will be somewhere, one of the variables have a degree that's not exactly 1.